Okay, so a couple things. I did figure out the licensing issue, so I'll probably just upload this as a short, separate video. But from this window you can see right here before this closes, clearly it did run one of the designs. This was the lowest angle of attack, lowest Reynolds number case, so it's generating very low forces. But that's to be expected from the low velocities involved. So we are going to load this design manager project, and you need to add one option to the bottom here. I've saved this for myself as a special thing, but it should look like this in the command lines. It should look like Star-CCM plus dash server dash CPU bind dash DM project dash DM no share. The no share is the part you'll probably need to add. This makes it so that the design manager by itself won't use a license, which is great. It will still need a license to run the designs, but the manager itself will not require one. We're going to click OK. This should open up the project. Give it a second. And then there's a couple extra things to change from the way I had this previously. It might yell at you a little bit because it's not actually told to look for any license servers. That's okay. It shouldn't need one. This did work for me. And I am not connected to the SJSU VPN at the moment. So this should work just fine for pretty much everyone, whether you are or aren't connected to the VPN. So this is our thing. We already did run one of these. So we can see that that did work. So let me point out the thing that needs to happen here. What I did was I went down here into tools, into compute resources, and made a new compute resource direct. Just to make abundantly clear that it's a new thing. I think I could have just used the default direct, but in any case. And I took the arguments from as if I were opening a simulation with the power on demand licensing, and did make a couple of changes, but I basically copied this. Okay. I'm going to put this in default direct so you can see what I did without editing the results here. So there's a couple things you need to delete here. You need to delete the dash NP whatever number of processors you have. And you need to delete the server. The rest should be okay. So previously I changed this so it was running with the new one I made. I'm going to change it back to default direct. And then it should just run based on the settings we used, one simultaneous job. In my case, 14 compute processes, so 14 cores. It will attempt to check out a power on demand license, run each design, and then close that design. There's one extra thing that we're going to do here, I think, and that is going to be, where'd it go? Design table, responses. Where the heck was it? The answer is what I'm looking for is where to save the file. Because these files are small enough and are generally compact. Save simulation files. That I would like it to save these. I would like it to save every single design file. There will be 44 of them. There'll be some number of megabytes apiece. I don't even remember. Reference properties. They'll be about 40 megabytes apiece. So you're talking 40 of them. You're talking a little bit more than a gigabyte. You don't have to save all of them if you don't want, but if you don't tell it to save the file, it won't. It will delete the simulation file when it's done, only saving the information that you told it to. Oh, I think I messed this up, didn't I? Well, okay. So, I need to make more plots. This is going to be... Wait a second. Where is my... Sorry, 1 second here. Where did that go? Responses. Because I'm going to bet that this plot does not look very reasonable by and large. Yeah, it doesn't. Okay. Well, we can just copy and paste this a whole bunch. And delete the not appropriate ones for each of them. Okay. A little bit tedious, but drag versus AOA, and I'm going to delete everything that's not drag versus AOA. This is going to be moment leading edge versus AOA. I'm going to delete everything that is not moment about the leading edge versus AOA. This is going to be XCP versus AOA. And again, deleting everything that is not actually messed up when I was typing that one. This is going to be Y. CP versus AOA. Ditto this. Okay. So that should be lift versus AOA plus all the others. So this is going to be lift versus Reynolds number. Rinse, repeat. Note, I should have done this properly the first time. This process is normally not necessary. I just accidentally added new data series, so new lines on a plot, instead of actually making multiple plots. That was my mistake. I just made more lines on the same plot, which I should not have done. It's going to be moment about the leading edge. Underscore LE versus Reynolds number. This is going to be XTP versus Reynolds number. P versus Reynolds number. And I messed up a little bit because I technically need one more. Where is it? Here we go. Y underscore CP versus Reynolds number. And then data series, I can delete everything except for that. And where's my lift versus? Lift versus AOA. Here we go. We can delete all these. There we go. That's better. Okay, now I'm not going to let it finish, at least not on screen. But we should be able to hit run study, and it should actually start to look at these things. Okay, so it's preparing to execute design 2, preparing the input files, it's checked out a task ID and a job ID, it's starting the design, it's launching the process, and if it doesn't crash in the next like 10 seconds for whatever reason, that's probably running. and I'll, because I'm obviously sitting next to this computer that it's running on, I'll be able to tell when it's actually running, like actually running the process, because I will hear the fan spin up. The computer will start to get warm. This did clearly actually run and change things to some degree. Oops, sorry. Yeah, it did run and change things to some degree. The pitching moment changed by quite a lot, and the forces got a lot smaller. So this did crank down the Reynolds number quite a lot. We can see what it was baseline at about a Reynolds number of a little bit less than 5 million, and then what it was at 100,000. And I can hear the fan spin up, so I do know that it is running actually. And now we just give it time. So that said, this is a way to, in conjunction with the previous video, very rapidly iterate, or as rapidly as you can given the hardware constraints, iterate through many different simulations of different permutations of a similar setup. As long as you can define the different permutations in some way with parameters, you can use this method. It doesn't just have to be geometric. It doesn't just have to be basic input parameters. You could also apply heat loads. You could get endlessly creative with this stuff. The program is very, very, very flexible in that respect. But as with all things simulation, garbage in, garbage out. If you don't set it up right, your results will be gibberish. So do be careful about setting things up. And before you just run all 40 of them or whatever, double check your settings. Make sure the first couple of them make sense. Especially make sure the first couple of them at a different angle of attack are actually at a different angle of attack. Um, and to do that, we can probably take a look and check a couple of scenes here. And hold on, where is it? Scenes. I think if you check the scenes, it should save them. I think. There are more advanced things you can do with this. Certainly. Many more advanced things you can do with this. But this is where we're going to leave it for now. But note the very last thing I did was I'm going to save this as hard copy, let's say. I'm going to have it print out the scalar and the vector scene as a hard copy, so probably as a PNG or JPEG, so we can take a look at them when it's done with this. And I'm pretty sure the first simulation just finished, so we'll actually wait a second for that, and let me pull up the directory where this is saved. Open file location. Pitching, lift, drag, plot. Yeah. Oh, it did save the simulation though, so that's good news. The I don't think I got there early enough where it actually decided to hard copy the scene. But if you wanted to look at things associated with the simulation, you go to the file. It'll make a folder named, or it'll place the folder wherever you have the design manager file saved, and it'll inside of that folder have the information and files associated with your design, with the tests that it's running. You can see here it actually saved a full-on simulation file of about 42 megs, uh, that should contain everything: the geometry, the mesh, the whole 9 yards. One thing I forgot to mention, kind of important, it's a little bit implied. It will automatically rerun any and all operations that it needs to in order to execute the design. Let me repeat that. It will rerun automatically any and all operations that it needs to before it actually executes the design. So you change the Reynolds number. It may or may not actually be remeshing, because it may not need to at this point, but the moment it changes the angle of attack, it needs to remesh, right? Because you've changed the geometry of the file. It will remesh. It will remesh and rerun. So depending on how much time it takes to run versus mesh, there's a whole bunch of cost-benefit things to if something like this makes sense. For something two-dimensional, for something lightweight like an airfoil and relatively quick to run, that's running in a matter of minutes, not hard at all to actually make this work. This sort of approach, this design manager approach, could be prohibitively expensive depending on the resources available and the problem at hand. It's really a case of the right tool for the right job. So, that said, I think that should be everything. With that, we're going to close out this video. I'm going to start to upload them, and you can take a look at these before class.